So welcome everyone to, I guess this is the fourth of this series of the Midwest Computability Seminar in Exile. And our speaker today, very happy to have Chris Porter talking about the effective dimension and intersection of random closed sets.
All right, thanks Dennis. Thanks for the invitation to the organizers. I missed the days of being able to drive down the road from Notre Dame to Chicago and hit the Midwest Computability Seminar. Those are long gone. I guess, I miss the days of just being able to drive anywhere, but okay, that's not to see you all, whatever. Let's get going. So this is joint work with Adam Case. Adam's a student of Jack Lutz here at Drake on the computer science side. And so this is some of the stuff that we've been working on. So when you live in Iowa and you care about computability theory, you can't avoid effective Hausdorff dimension, right? 45 minutes up the road is Ames, and that's where a lot of stuff's been happening. So there's been a lot of developments. Lutz, Stull, so Jack and Neil have been proving theorems that are really powerful, show the value of effective methods for getting new insights in classical mathematics. I don't claim to be delivering anything of that stature or quality, but what I'm hoping today is to show you that in the context of random closed sets, effective dimension, we already know a little bit about what that tells us about members of random closed sets. And in fact, that can be refined. And so I'll talk about how that was refined by Adam and myself. So what do we know? So David Diamondstone and Bjorn Kils-Hansen have a paper on members of random closed sets, and then that's a conference version, and then Galton Watson random closed sets or something like this, probably about, I don't know, a little more than 10 years old. And what those papers establish is a relationship between effective Hausdorff dimension and being members of certain kinds of closed sets. So the random closed sets that I'll be talking about really grew out of a research group from the previous iteration of AIM from 2006, spearheaded by Senzer, and a bunch of papers grew out of that. And I think there's still quite a lot more to say about random closed sets and connections to dimension and other areas. So hopefully, again, you'll see some of that today. Here's the result that we have from David and Bjorn. So if a sequence has effective dimension greater than or equal to some value gamma, and I'll define these if you need reminding when we get there, then it's a member of a certain kind of random closed set where the randomness of the closed set is determined by this parameter gamma. Okay, so that's we'll specify that in a little while. And then moreover, if I have a member of a random closed set with the same parameter gamma, then that puts a constraint on the dimension of the members. And so I have this, gamma now serves as a lower bound. And it's not an if and only if here. So this was open for a while. And I mean, depending on how you think of questions being answered, it's still kind of open because the answer is unpublished due to Jason Root, and someone other than Jason looks like they're going to have to publish it to make that work. Okay, so we know that this is not, we don't get a necessary and sufficient condition. So having dimension greater than or equal to gamma is sufficient, but it's there are sequences with gamma dimension exactly equal to gamma that are not members of these random closed sets. So right at that boundary point, some weird stuff happens. Okay, that's really not, we can work around that, and I'll work around it today. And that parameter, so gamma here is going to vary from 0 to 1. The value 2 to the minus gamma is a survival parameter for a certain kind of process of pruning the full binary tree. So this is a Galton-Watson process. Okay, so that's what we know. One of the things you can immediately extract from this is not, I mean, we'll see this result stated in this way, but being a member of one of these random closed sets, now I need my gamma to be bigger than 0 so that I don't include the full binary tree. The members of random closed sets for this range of families, they're all Bernoulli random closed sets. And again, I'll define that shortly. That's just the same as the collection of sequences of positive Hausdorff dimension. Okay, so members of random closed sets, positive dimension sequences, those are the same. And what I want to do now is further refine that correspondence. And I'll do so by showing how the dimension of a sequence relates to how intersectible the random closed sets are that contain it. So what's that relationship? And the claim is like the effective dimension of a sequence is inversely proportional to how many intersections are possible for the family of random closed sets that contain it. Okay, so not every sequence of low dimension, they are not in random closed sets with low amount of branching. You need lots and lots of branching in a random closed set to hide these low dimensional sequences. And then that high amount of branching in turn implies that these closed sets can have an intersection. So if I have a random closed set which doesn't branch very much, then that means that it's not very likely that the intersection of these two random closed sets with this low branching will be non-empty. Okay, and all of this can be made kind of quantitatively precise, which I think is pretty exciting. Okay, so this idea of this notion of the degree of intersectibility is something that I'll define at the end, but that's really how I'm thinking about it. Dimension is like putting a roadblock on or a constraint on the amount of intersectibility of the kinds of random closed sets that you find those sequences in. Okay, so I'm gonna give some background, fill in some details, especially the random closed set stuff. I mean, this isn't a hugely popular area in the field, and so I think we all need some refresher on that. Then I'll talk about work on the intersection of random closed sets that was done by Doug Senzer and Rebecca Weber, 2010, I believe, 2008, some kind of early, back 10, 12 years ago, that was inspired some of the questions that we were looking at initially, and then out of which this issue of intersectibility and dimension came out. And then I'll spell out what exactly that relationship is, and then say a tiny bit about where could we go from here. All right, so on to the background. I take it that you all are very familiar with the notion of effective Hausdorff dimension, so I'm not gonna say very much here. Here, if we take the prefix-free Kolmogorov complexity K of a binary string, and so now look at the first n bits of an infinite sequence, divide that complexity by n, and now I want to take the lim-inf of that. So what is this telling me? So k of x of up to n is something like how compressible the first n bits of my sequence is, and that value could be really, really close to 0, or maybe even exceed n. And by and large, right, those are the bounds that you're looking at, from 0 to n. And so this ratio is going to be a ratio from 0 to 1. And so now we want to study where does this thing go, right? And so infinitely often, does it get kind of closer and closer and closer to 1, or closer and closer and closer to 0? Almost all initial segments are close to n, and so on. Okay, so this really tells you something about the density of the information content in a sequence. How packed is this sequence with information content? Now let's do some discussion of random closed sets. And the way that Senzer and company defined the original approach to random closed sets was with a coding mechanism. So what we want to do is we're looking at closed subsets of Cantor space, and we really want to represent these as sequences. Now there was some pushback early on, and I think this is reasonable that coding sequences can be ad hoc, and we don't want to have results that depend on the choice of coding that we've come up with. Maybe we should work with a more natural, native approach to randomness by looking at, the closed sets as random objects in and of themselves, not coded by random sequences or whatever. But nonetheless, this is really useful, easy to work with sequences. So what we want to do is, for every closed subset of Cantor space, we want to represent it as a ternary sequence. And so what we do is, at every given node that's extendable in the closed set, right? At each node, it's extendable, so we know it has some extensions. Either it has a left extension alone, only a right extension, or both extensions. And so those are 3 events that you'll code with a 0, a 1, or a 2. And so now if you have a closed set, draw your closed set, and then just go through all the extendable nodes one at a time and ask, what are the extensions? Is it just to the left, just to the right, or both? And then you can write down your sequence 0 and 2, and so on. And then from such a sequence, you can recover the closed set. So I have the full, potentially the full tree, right? If I have all 2s, but now I see that, initially I have a 2, so that means at the root I include both extensions. And now I just move through all of the live nodes here. There's a 0, so I only branch to the left. I move over here, there's a 2, I branch to both. I have a 1 there, so I include the right extension. Now I skip over, right? I had to skip this node over there. So I skip over to, here I see there's a 1, so I extend, and so on. Okay, there's another approach to this where we just hit every single node, even if it gets disconnected from the root. And this is referred to by Sensor and company as a kind of a ghost code approach. And so now a sequence can have, a random closed set can have potentially infinitely many ghost codes because you only care about the component connected to the root. And so whatever happens after the root could be bizarre or whatever. And so a sequence is random if it has a random ghost code. And that definition of randomness will be the same as this one, give rise to the same collection of random objects. But now we're going to do things in more generality. We want to look at different measures. So I don't want to just look at measures, kind of a uniform measure, say on 3 to the omega. So we'll say, first of all, we want our measures to all be computable, right? What else are we doing here? Well, no, okay, you can look at non-computable measures, but I just want to look at computable measures. So this will be a map from a ternary string to the measure of its cylinder set that's uniformly computable as a real value function. And just for shorthand that I'll use in like the next few slides, I'll write mu of sigma I followed, given sigma. This is for 0, I equals 0, 1, and 2, just the conditional probabilities of the 3 events, branch to the left, branch to the right, or have both. What are the measures we care about? Well, I want to look at really 2 classes. So first, Bernoulli measures on 3 to the omega. So a Bernoulli measure, you can think of it as a sequence of trials where each trial has the outcomes that are equiprobable. So it's an independent sequence of events with identical distribution. Well, now I have 3 events, right? So I should have 3 probabilities. We want the probabilities to add to 1. So I just have to specify 2 parameters, the probability of a 0, which is P, the probability of a 1, which is Q, and the probability of a 2, which is just whatever's left over. And that will be a Bernoulli measure on 3 to the omega. And in the case that these 2 parameters are computable real numbers, then I get you can show that this gives you a computable measure in the sense defined on the previous slide. More to, restricted, I want to look at what I call, or whatever, it just seems like a reasonable way to pick these out, symmetric Bernoulli measures. So these are measures where the probability of branching to the left or to the right are the same. So for all practical purposes, we just care probabilistically, do we have only one branching extension or both? And so now the probabilities of 0s and 1s are both P, and the probability of a 2 is 1 minus 2P. Right? So that's just setting P equal to Q in the Bernoulli case. And then now I only have a single parameter, so a computable measure in this case is just one where the parameter P is computable, of course. And then we just define random sequences in 3 to the omega in the way that we all do when we define randomness. So we have a collection of uniform, open, uniformly, effectively open subsets of Cantor space. I'm starting to think about something else. So we have this collection of open sets, the single procedure that enumerates the cylinders that make up those. And here now we're looking at they're all subsets of 3 to the omega, so not Cantor space. And for our measure mu, which will be one of the kinds from the previous page, that's all we care about. We'll require that the mu measure of u to the I is u sub I is 2 to the minus I. Right? So that's at each level of the test, right? These are like critical regions for statistical tests performed on members of 3 to the omega. The critical regions are getting smaller and smaller. So there's kind of level of significance, a half, a fourth, an eighth, whatever. Martin Loeb's idea of sequential randomness is to test at all levels of significance simultaneously. So then a sequence passes the test if it's not in the intersection, so you escape at some level of significance, you're not in the critical region. And then a random sequence passes all such tests. Okay, so that's fine. And then I'm going to relativize these because we want to look at when we intersect random closed sets, we want the closed sets to be random relative to each other. So we need the codes to be random relative to each other. Okay, so we'll just assume that we know how to relativize this, which should be really straightforward. Right? Where does the randomness now transfer over to the space of closed subsets? So we'll use K of 2 to the omega to be the closed subsets of Cantor space. Then we'll just say a sequence is random if it has a random code in 3 to the omega. And there's only one code, right, of the extendable nodes. And so this is a reasonable definition that, they got Sensor with Barbolius, Broadhead, Doshti, Weber got a lot of mileage out of it. they studied, the initial paper was just for the case that P equals Q equals a third. So the probability of branching to the left and to the right, or both, those are all equiprobable, 1/3, 1/3, 1/3. So it's a uniform measure on 3 to the omega. And that was kind of the baseline for this investigation. And then Sensor is the intersection of all of the projects on this. There's many other papers with like a big list of names, but if you look at who's on all those projects, it's Doug. So he pushed this topic into other, looking at different probability measures. So these probability measures, the Bernoulli measures, the symmetric ones, and even ones where the probabilities change level by level. He's done work with all of those. This definition is robust. So I remember back in the day when I was a graduate student and kind of the glory days of the Cholak seminar. It was myself, Logan Axon, Josh Cole, Sean Walsh, and Stephen Flood. We've all, it's like, good job, Peter. You kept this all in the fold. And at the time, Logan was working on the LR degrees, which were really hard. And at some point after the AIM meeting, Peter said, here's this definition of random closed set. Here's this large book on random closed sets, classically by this guy Molchanov. Make the two connect to each other in some way. That's really good advising. Like, here's a big question, and now come back a couple years later and solve these problems. So Logan did that. He wrote a really nice dissertation and got some good publications out of it, where he showed that you can naturally define randomness on the space of closed subsets of Cantor space, or of a large variety of locally compact Hausdorff spaces by looking at this different topology, the hit or miss topology, maybe the Fell topology. So here you're an open subset of closed sets is given by specifying a finite collection of compact sets that the members of the closed set of the basic open have to intersect, and a collection of open sets that your members of your basic open set have to avoid. So you hit the compact sets and you miss the open ones. I believe that's right. And so that's when you define the appropriate measure on these things, then you can show the equivalence with, say, the standard 1/3, 1/3, 1/3 approach, and then there's more variation in there. Then also the Diamond-Stone Kioss-Hansen approach I've already mentioned, where you're, instead of looking at random closed sets, where you're considering essentially extendable nodes, you create trees as a part of a process of pruning, like the full binary tree. And if the resulting tree is infinite, then the set of paths through that tree will be a closed set. And if the tree is finite, you get the empty set, but condition on the closed set that you get being non-empty, you get the same class. So that was a really nice approach that Kioss-Hansen and Diamond-Stone gave. Again, the same equivalent definition. One of the conventions, this goes back to the Sensor and company approach, is to work explicitly with measures on 3 to the omega and really just say, I don't know what the measure on the closed subsets of Cantor space really looked like. So whatever that measure is, call it mu star, but really when I'm always going to just go back to the coding space and work with the measure there. I know how to enumerate the closed sets in a much easier way. It's just nicer to work on. So there's this kind of transfer of randomness from 3 omega to the closed subsets of Cantor space, and the transformation preserves randomness from mu random codes to mu star random closed sets. So really, in my mind, these are identified with each other. But if the notation's consistent, the asterisk should suggest we're working with closed sets. The absence of it is we're working with the code. And then let me say just a little bit about these symmetric Bernoulli random closed sets. So these are nice because where does the symmetry come in? Well, if I take a closed set that's random for one of these measures, right, I look at the code. If I just swap the zeros and the ones, right, I'm swapping equiprobable events. I've preserved, like I'm not getting a new measure, and so this thing is closed under essentially mirror reflections. So there's a nice symmetry there. This is certainly there's nothing too special about them other than that, but these are what Sensor and Webb are really focusing on. There's extreme cases that are kind of, we don't want to avoid these per se. It kind of helps to think about how the parameter, the single parameter as that varies, affects the resulting randomness. So as P ranges from 0 to 1/2, the amount of branching will vary, right? So what are the extreme cases? If P is 0, right, remember I have branch to the left, to the right, those are both probability P. both branches is 1 minus 2p. If p is 0, then every outcome is both branches. And I have in the sequence space, my measure is just concentrated on the sequence of all 2's. And so in the space of closed sets, there's only one closed set. It's just Cantor space. So that's not really that interesting. But that's the limiting of how much branching you can get, all the branching. And then on the other extreme, if p goes to 1/2, now the probability of a left branch or a right branch, those are going to 1/2, and the probability of both branches goes to 0. And so in the limiting case on that side, I'm just looking at basically building a closed set as a singleton by tossing my coin and just, right? And so now there's no branching at all, and so I'm just getting a sequence of 0s and 1s that's random. So the resulting closed set is a random singleton. Okay, so those are the two extremes. Okay, so there's lots of intersection on the side. When I intersect a Cantor space with itself, it's always non-empty. That's great, of course. If I intersect a random singleton with another random singleton, I mean, there's no chance of getting a non-empty intersection, right? Because I'm going to have two different sequences. So intersecting singletons is not very fun. Okay, so that's a little bit of the picture of how this branching varies, and it turns out to be quite productive to think about what happens when you vary this branching. Okay, so now I'm going to throw out what Senzer and Weber did, and this is really, I think, very similar flavor. This result is the flavor of this result is very common in some of these papers. This is a very Senzerian result, a very Senzer-like technique, if that's a word. So let's take two Bernoulli closed sets and ask when can we intersect them and get another closed set, a non-empty closed set. Okay, so what we want to do is we want to fix 4 parameters. So the first closed set will be PQ, so branch to the left P, branch to the right Q, branch both 1 minus P minus Q, and then RS 1 minus R minus S. Okay, so those are the two kinds of closed sets. Was there a question or just like a sound? Okay, that's fine. If you want to stop me for anything, that's fine. So now, what are the possible cases? And this is the game you play. You just start looking at the first level of the trees and what are the possible things you can get if I have this closed set with these probabilities, this closed set with these probabilities. Look at what happens at the first level of the tree, and then give kind of a recursive or a kind of inductive argument, assuming above that first level, the intersection is non-empty, and then you get some equations and with kind of parameterized by the number of levels that you're looking at, and you take some limit, and then you get these like crazy formulas like these. Okay, here's a constraint on all these parameters. If P plus Q plus R plus S is greater than or equal to 2 plus PR plus QS, these things are never going to have a non-empty intersection. So they never intersect. And what is this? It's just so you can, if you were to kind of trace this, and we won't here, this is a technical condition that just says there's not enough branching in these closed sets to guarantee together that they're going to line up infinitely often to give you a path through the result. I mean, I'm always going to get a finite tree when I try to do this, right? If these are random relative to each other, then I'm always getting a finite tree. However, if that inequality goes in the other way, I got a fighting chance. I have a fighting chance. So what this means is again, there's constraints here, but now there's a positive measure collection of pairs of closed sets. When I look at the intersection, I get an infinite tree. And now the probability of 2's, okay, so I want intersections correspond to lots of 2's. So if I have, as these probabilities are getting, I'm gonna say, the probability of 2 is getting smaller, these things are getting smaller here, down here in the denominator. So this whole probability is getting larger, and this is the probability of no intersection. So now as I'm wait, hold on. In any case, I'm not gonna like think of this on the fly. There's a kind of direct connection to how much branching is in these things and this probability. More branching gives me a better chance at having this non-empty intersection. Okay. I'm only gonna use these formulas in passing. And then lastly, what's cool is they figured out what the measure is that you get from the intersection. When it's non-empty, then I get this parameter. So now the probability of branching to the left is kind of a, almost like a kind of, I don't want to say convolution, but it's like this mixture of the left branches of both and the right branches of both. P plus R minus PR, Q plus S minus QS. And then the probability of both is 1 minus those two terms. And now we have a sufficient amount of branching, and this is 1 minus this probability over here. That's the measure of the pairs of closed sets that have a non-empty intersection. Okay, so we get another Bernoulli random closed set. Hooray. Thank you, Doug and Rebecca, for that hard work to pull all this out. Not very informative, right? All these parameters floating around. So one of the things that, as a side note, this is really how the project started for Adam and myself, was they left open a question. What about the converse? If I have the constraint that allows an intersection to be non-empty, and I have a random closed set for the resulting parameters, can I pull it back to a pair of random closed sets whose intersection is the given one? And the answer is yes. So that can be done. And so we answered that question, and in the midst of it started looking at multiple intersections, and that's going to lead us to kind of some cool stuff. What happens when we only have a single parameter? So I'm intersecting a p random closed set with another p random closed set. That's kind of a cool question. It's messy when p's and q's and r's and s's are all floating around. So let's just boil it down to a single parameter. The closed sets are of the same kind. And all of those inequalities from before that look kind of, just not very informative, become something very kind of crisp. So now, if I have relatively p random, so p random closed sets, so the probability of branching to the left and the right are both p, the probability of both is 1 minus 2p, then I get 3 cases. So either if p is bigger than this weird value, which is about 0.3, 1 minus root 2 over 2, that's not enough branching. P is getting closer and closer to a half. So if you're above 0.3-ish, then that's not enough branching for an intersection to we only get a finite tree from 2 randoms. If, however, we're below that threshold, then we have a fighting chance. And again, as p goes to 0, then this probability goes to 0, and so the probability of empty intersection is going to 0, and so the probability of a non-empty one is 1 minus this thing that's going to 1. And then lastly, what happens? What's the parameter? What do we get when it works? When there's a non-empty intersection, then it's this 2p minus p squared. And now you might ask, this is a weird number. Like, where does this come from? And really, it comes from this induced parameter 2p minus p squared, because for all of these measures, the parameter has to be at most a half. And so if 2p minus p squared is less than a half, that can only happen when p is less than 1 minus root 2 over 2. Okay, so that, as kind of magical as that looks, it's a kind of it's a very nice number to serve as the threshold. This it comes in a pretty reasonable way from these, this new parameter. Of course, you might say, like, why did we get that? I want to do more. I don't want to intersect 2, I want to intersect 3, 4, 5, and so on. So to do that, I don't want to look at relatively random closed sets or even pairwise ones. So I'll just say, I want each random closed set in my sequence of, say, n random closed sets to be random to the join of all the others. Well, I'm not joining closed sets, I'm joining their codes. Okay, so that really just amounts to the join of all of the codes being a random sequence by von Lomborg's theorem, which holds for Bernoulli randomness. Okay, so there's let's just say joint. I don't know what the term, if there's a better terminology, nicer terminology for this, but we'll just say, jointly. I think we were mutually relatively random before. Let's say jointly random. Okay, so here's the picture that we got from Senzer and Weber. For any parameter p in that interval there, from 1 minus 1 over square root of 2 up to 1/2, the p random closed sets don't ever intersect. Relatively random ones never intersect. But then down below, this is where they can with positive probability. Okay, so just to save ourselves from writing all of this out, we might say that it's not the case that 2 intersect when my parameter is in here, but it's possible that 2 intersect when the parameter is in here. I mean, maybe you could say, oh, this should be not possible, whatever. This isn't modal logic, this is me being lazy. So the intersection of 2 relatively random closed sets no empty intersection, possibly a non-empty intersection here. What I was hoping for, what would be a nice thing to have, is a sequence. Again, there's no reason to think this is the case. A sequence of values. So maybe this is p sub 1 here, and now I get p sub 2, p sub 3, so on, where the intersections behave like 2 don't intersect here for any random closed set with a parameter. No 2 intersect. 2 can intersect, but 3 don't. But then over here, 3 can intersect, but 4 never do. 5 can intersect, but 4 can intersect, but 5 never do, and so on. Okay, so I want to be able to locate the kind of level. This is where intersectibility is going to eventually emerge, right? Does the amount of intersection vary as I move along these kind of subintervals? What marks the boundaries between these subintervals? So let's look at 3. Let's look at 3. So this is the strategy, right? You just take 3 relatively random closed sets, assume that they have a non-empty intersection. So it would be in that third case of like the corollary of the Sensor and Weber. Well, if the 3 have a non-empty intersection, then the first 2 certainly have a non-empty intersection, and we know what the probability, the resulting measure is. And now we intersect the third one, and we use the other Sensor-Weber theorem, and then plug everything in, and we get now that the resulting parameter should be, assuming non-empty, 3p minus 3p squared plus p cubed. Okay, so this looks binomial-ish. It's good. And then if you want to figure out what about these probabilities, right? So, what about in that third case, you needed to have what, p plus q plus r plus s less than all that. When you plug all that in, there it is, right? This is what in the case that we're intersecting these 2 kinds of random closed sets, this is what you get. 3p, that same parameter is less than a half. Well, yeah, of course it has to be less than a half if we're getting a parameter of a Bernoulli random closed set where p is between 0 and a half. Getting it bigger than that won't work. Okay, so that constraint becomes like very tangible, right? I mean, we already had that constraint in a sense. Okay, now how does this work in general? In general, if you were to work this out for each n, right, we get a sequence of polynomials. And for n plus 1 jointly random closed sets, okay, so 1 is random to the join of the other n. If the intersection of the n plus 1 is non-empty, then if I intersect the first n, I get that is empty, non-empty, and it's random relative to the parameter in the nth, so the nth polynomial with p plugged into it. And then I intersect one more, and I'm going to get this p plus f of n of p minus p times. Okay, some weird relationship shows up, but this should be the parameter for the n plus first level, and that should be the value obtained by the n plus first polynomial in my sequence. So this is the relationship that holds. So the n plus first polynomial can be defined in terms of the nth one in this way. So you see it there. I don't need to read it. And then moreover, that other constraint that when I add in p plus q plus r plus s is less than yada yada yada, that just amounts to saying that for each of the n's, this polynomial, when I plug in my parameter, has to be smaller than a half. Okay, so let's figure out what these polynomials are. So the case that n is equal to 0 is the case that I'm intersecting, I guess, let me think here. How did I say this? So n plus, so basically I'm not intersecting, I just have the single thing. So f sub, I'm going to be sure, it's either f sub 1 is p or f sub 1 of p is p, or maybe this is equal to 1. It doesn't matter. There's an initial case that's easy to figure out. I just didn't get the right one, but it doesn't matter because I have the recurrence relation here. And from this, you can prove inductively that these are really nice polynomials. 1 minus p to the n, subtract that from 1. The second constraint says, well, yeah, I need this polynomial to always be below a half. But if I solve for p, that just means that p has to be 1 minus 1 over the nth root of 2. Wow, so these should be the thresholds. And that's exactly what we get. So for this sequence of polynomials, given n jointly random closed sets, when do they have an intersection or not? Well, if p is bigger than the nth value for intersecting n of n, if it's above that nth threshold, then we'll never get a non-empty intersection. It's just not going to work out. So P has to be on the other side of it, to the left. I need more branching. I need more branching. And then I can find the probability. And in fact, it's computable from the polynomial as well, which is really quite nice. And then what is the parameter for the resulting measure? Well, it's just the value of the polynomial. Okay, so I have this really clean way of, as I take more and more intersections, I can see what the kind of in a very uniform way, how much randomness, how much branching has to take place, right? So this is f sub n of p, f sub n of p, 1 minus 2 times f sub n of p. So that's what this looks like. And so there we are. There are the thresholds, right? So they're just 1 over the square root of 2, the cube root, the 4th root, the 5th root, all the way down. And then as a side note, well, can I do the converse? Can I take a random closed set for parameter p and ask, can it be obtained as the intersection of n jointly random closed sets for some parameter? And the answer is also yes. And to invert this process, happily, we invert the, we invert that polynomial and plug in our parameter, and that will tell us exactly what the parameters should be. There's some choice of random closed sets that will then give me the intersection in this way. Okay, so that works out really nicely. And now we'll tie this into dimension. So this is where I have to really revisit the Coase-Hansen-Diamond-Stone stuff. So as I said before, they defined the dimension of random closed sets, but it was relative to, or just in terms of the survival parameter. And I haven't been talking about random closed sets defined in terms of the survival parameter. I've been talking about them in terms of a Bernoulli measure. So we have to translate the survival parameter talk into Bernoulli measure talk. Okay, so the process that they use, I mentioned this before, fix a gamma between 0 and 1, start with the full binary tree, and move edge by edge, length lexicographically with your scissors, toss your coin that comes up heads with probability, 1 minus 2 to the minus gamma, and cut an edge if your coin comes up heads, leave it if it comes up tails. So in the case that gamma is 0, you're never cutting anything. In the case that gamma is 1, it's a probability 1/2 of cutting, but that's too high of a probability. You're going to always get a finite tree after some point. Okay, so the probability that an edge remains is the survival probability. That's 2 to the minus gamma. Now, if you think about mu sub p random closed set, right, at each point we have probability p of branching to the left, p of branching to the right, 1 minus 2p of both. So now I have to think about what's the associated survival probability. So suppose I have this node that's an extendable node. So it will have survived the process. It will have survived because of one of two things happened. Either we had a 0 in the code, the corresponding coding location in the code of the closed set, or we had a 2. So we had a 0 or a 2, probability p plus probability 1 minus 2p, and so I get 1 minus p. Okay, so now I want to solve for the gamma, because I need to write the survival. 1 minus 2p is 2 to the minus gamma. Let's just solve for it, minus the log of 1 minus p. Okay, so here's their result that I posted in the, like a rough sketch of it in the first slide or one of the early slides. Take your parameter gamma. If x is a member of a random closed set with survival parameter 2 to the minus gamma, then the dimension of that sequence has to be greater than or equal to gamma. If the dimension is greater than gamma, then you're in some random closed set with survival parameter 2 to the minus gamma. And then the caveat, at the boundary where dimension of x is equal to gamma, it's complicated. It's tied to gamma energy randomness. Okay, so that's something else. Okay, let's plug in now into gamma, or the 1 minus, so minus the log of 1 minus p, these special thresholds. And it turns out minus the log of 1 minus p applied to 1 minus 1 over the nth root of 2 is just 1 over n. Wow, I was very happy to see like a 1 over n. Wait, that's telling me then dimension threshold about 1 over n corresponds to intersections of n being possible, but more than that, not necessarily. Okay, so now we have, like in this context, if we just move along these boundary points, not just 1 minus 1 over root 2, but for every single one in the sequence, if you're in a random closed set at one of these levels, now I have the dimension of all your members is 1 over n. at greater than or equal to it. And if your dimension is greater than 1 over n, you're a member of one of these intersectible random closed sets. Let's talk about this now. Let's make this precise. How should we define intersectibility? I mean, this is a bit, open to how we want to define it, but we chose to say the degree of intersectibility of a random closed set is the least n, it's the unique n, right? Where the intersection of n jointly random closed sets is possible, but the intersection of n plus 1 is not. So that's the place where it cuts off. Okay, so if a random closed set is 4 intersectible, then it's 3 intersectible and it's 2 intersectible, but it may not be 5 intersectible. Okay, so it gets cut off somewhere. So we want to kind of how much what's the most amount of intersectibility? And then the nice thing is we know that there's an actual cutoff. So that the fact that there are these numbers is a happy result. And then for an asymmetric Bernoulli random closed set with parameter p, we can then say, well, its degree of intersectibility, check which of these intervals, right, where the thresholds are, where does it fall? And now we say, oh, it falls between these two, and so it has degree of intersectibility n. Because on the other side of 1 minus 1 over the n plus first root of 2, we can't get n plus 1 to intersect. Okay, so that's the. And now let's put all the pieces together. So if I have a symmetric Bernoulli random closed set with a certain amount of degree of intersectibility, immediately I can say that degree of intersectibility is almost exact, inversely related to the dimensions of its members. Okay, so that's one of the Kios-Hansen results. And in fact, I can do a little bit better. So now you give me a sequence of dimension S. We have to be a little careful when the dimension is 1 over n. But let's say its dimension is, right, so because of what happens at those boundary points. If S is not equal to 1 over n for any n, then dimension S means whenever you're in a symmetric, so this thing is in symmetric, it has positive dimension, so it's in Bernoulli random closed sets. And how much intersectibility is bounded below by the floor of the reciprocal. And moreover, if I look at anything where the intersectibility is below that value, it can't be in any of these members. Okay, so this is the sense in which the dimension is like this roadblock, right, to how much branching is possible. And again, the branching is tied to intersectibility, but in a very tight way. All right, where do we go from here? Just a little bit more. A couple of things I've been thinking about where we could push this. So first of all, I know not too much done on energy randomness. These energy integrals show up in a few papers, Jan and then Bjorn Kios-Hansen, Jan Ryman. And then there's a paper that Joe wrote with Jason that gives a ample excess lemma-like characterization of energy randomness. But then there's a kind of in a forthcoming paper, we will show these other things. And then Jason, I mean, it's unfortunate because I don't think it's hard to finish this work, but I wouldn't want to, write a paper that's like ghost writing for Jason. So, I mean, it would be appropriate to extend these results in a context like this. Okay, so what's the exact relationship between energy randomness and degrees of intersectibility? Why is that related? Bjorn and David conjectured that energy randomness is exactly, for a given parameter, is exactly equal to being a member of a random closed set without these boundary issues. And that's exactly what Jason figured out. So what happens, there are, at the boundary, there are energy randoms that, like some energy randoms can have dimension equal to gamma and some of them might not. And so there's like this, not every dimension gamma sequence is gamma energy random. And that's what, the dimension results aren't optimal, but if you recast things in terms of what Jason did, then you get a tight, necessary and sufficient conditions. So there's, I think, that needs to be done precisely. And then another thing that I think is really worth pursuing, and I've done some of this, and I've had some conversations with Jack Lutz about this. So in a 2012 paper that Jack wrote with Elvira Mayordomo and a couple other folks, they looked at random subfractals of self-similar fractals. So they take the Sierpinski triangle, and as you look at levels of precision of the Sierpinski triangle, take out the middle triangle, and now you have 3 triangles left, and then take out each of the middles of those, and so on. What they ended up doing was looking at a way of deleting some of these subtriangles. And the way that they do it is they represent the process as what they call a coder selector game. So one person is coding the resulting closed sets. Basically what you have is at each level of precision, I have 1, 2, 3 big triangles. And then I say, selector, pick one of the 3 to delete. And so the selector chooses one. And then of the next 2, then they say, okay, there are these, now for each of those 2 triangles, you select one that you delete. What really this amounts to is that the coder, so to do this kind of randomly, the coder is going to be a random closed set, and the selector is a path through the random closed set. So what they were doing was reinventing the machinery of random closed sets in a different language. And then they went and found the dimension spectra of these various fractals, right? These are asking about the dimensions of the associated random closed sets. So translating all those results from what they were doing into the machinery of random closed sets, now we can talk about how intersectible are random subfractals of Sierpinski triangles, and how does that relate to the different probabilities of deletion and so on. Okay, so there's actually quite a bit to generalize there, and so I've done some of that. Okay, so that's the machinery of random closed sets. I think is really useful, and it just keeps showing up in kind of cool ways. Even with the AIM meeting that happened in late August, there were, or mid-August, whatever. That theme, you know, the value of those random closed sets, which really you can think of as being like the supports of random measures. There's some use for those that were, you know, it'd be nice to see those come to fruition. Thank you.
Thanks, Chris. I'll applaud for it. So are there questions? Comments? Just anyone has a question, just feel free to jump in. Well, if not, thank Chris again in whatever form he'll do, virtual or real.